Preparing for a controls engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How do you explain PID control, and how would you tune a PID loop in the field? PID control uses proportional, integral, and derivative actions to reduce error between a set point and process variable. I start by understanding process dynamics: dead time, lag, noise, and actuator limits. Proportional gives immediate correction, integral removes steady-state error, and derivative predicts change but amplifies noise. For tuning, I often use conservative gains, step testing, or vendor auto-tune, then validate stability, overshoot, settling time, and robustness under disturbances. While answering, focus on proportional, integral, derivative terms, tuning methods, stability, overshoot, settling time, noise sensitivity, actuator limits, and how you validate a loop after changes. Question 2. What happens during a PLC scan cycle, and why does scan time matter? A PLC scan is the repeated cycle of reading inputs, executing logic, updating outputs, and handling communications or diagnostics. The key point is timing. Logic does not run continuously in an analog sense. It updates once per scan. If a fast pulse is shorter than the scan time, it can be missed unless I use high-speed counters or interrupts. Good controls code accounts for scan time, deterministic sequencing, and safe output states. Make sure to cover the input read, logic execute, output update sequence, scan time implications, missed pulses, high-speed tasks, deterministic behavior, and why scan order matters during troubleshooting. Question 3. When would you use ladder logic versus structured text in a PLC program? I choose the PLC language based on maintainability and the task. Ladder is great for discrete I/O, interlocks, and electricians troubleshooting online because contacts and coils are intuitive. Structured text is better for math, arrays, recipes, state machines, and repeated logic. Function block diagrams work well for process loops. In real projects, I keep safety and core interlocks clear in ladder, use structured modules for complexity, and document interfaces carefully. In your answer, compare ladder, structured text, and function blocks by readability, maintenance audience, math-heavy logic, reusable modules, online troubleshooting, and standards within a plant. Question 4. A motor is not starting from the HMI. How would you troubleshoot it? The fastest approach is to split the problem into command, permissive, power, and feedback. I verify the start command reaches the PLC, then check interlocks like e-stop, overload, guard door, pressure, or drive fault. Next, I confirm output status, contactor coil voltage, or VFD run command, and motor power. Finally, I validate feedback, auxiliary contact, speed, or current. I avoid forcing outputs blindly. I use drawings, trends, and safe lockout practices. Be sure to mention a systematic troubleshooting path: command signal, permissives, PLC output, starter or VFD status, wiring, feedback, drawings, electrical safety, and avoiding unsafe forcing. Question 5. What key parameters do you configure before commissioning a VFD? A VFD controls motor speed by converting fixed AC to DC and then synthesizing variable frequency AC. Before startup, I check nameplate data, voltage, current limit, acceleration and deceleration ramps, minimum and maximum frequency, control source, reference source, and stop mode. I also verify motor protection, braking requirements, and grounding or shielding to reduce noise. For pumps and fans, VFDs save energy, but poor tuning can cause trips or mechanical stress. While answering, cover operating principle, motor nameplate setup, acceleration ramps, control and reference sources, current limits, braking, fault diagnostics, grounding, shielding, and mechanical load considerations. Question 6. What is the difference between open loop and closed loop control? Open loop control acts without measuring the result. Closed loop control uses feedback to correct error. A timer filling a tank is open loop. A level transmitter driving a valve through a PID loop is closed loop. Closed loop handles disturbances and model uncertainty, but it needs reliable sensors and stable tuning. I also consider response speed, noise filtering, actuator saturation, and fail-safe behavior before deciding which approach fits the process. Make sure to define feedback, set point, process variable, disturbance rejection, sensor reliability, stability, actuator saturation, and when open-loop control is acceptable despite less accuracy requirements. Question 7. How are safety circuits different from normal PLC control circuits? Safety functions should not rely on a standard PLC unless it is a certified safety PLC with validated architecture. Emergency stops, light curtains, and guard interlocks need defined safety ratings, redundancy, diagnostics, and controlled reset behavior. I design using risk assessment, ISO 13849 or IEC 62061 concepts, and safety relays or safety controllers. The key is predictable de-energization to a safe state with documented validation and no easy bypass. In your answer, distinguish standard control from safety-rated control, covering risk assessment, safety relays, safety PLCs, redundancy, diagnostics, reset logic, safe state, validation, and documentation. Question 8. Why is 420 mA often preferred over 0 to 10 V for analog instrumentation? 420 mA signals are less susceptible to noise. They allow for long cable runs, and they provide a built-in signal range to indicate faults, like a minimum current drop. This makes them more reliable for industrial applications. 4 to 20 mA is my default for industrial analog signals because current is less sensitive to voltage drop and electrical noise over long cable runs. The live 0 at 4 mA also lets me detect broken wires or failed transmitters. 0 to 10 volt is simpler and common inside panels or short distances, but it is more noise-prone. I always check scaling, loop power, grounding, shield termination, and fault handling in the PLC. Be sure to compare noise immunity, cable distance, live 0 fault detection, loop power, scaling, grounding, shielding, input modules, and practical use cases for each signal type. Question 9. What makes a good HMI or SCADA screen for an industrial process? A good HMI helps operators make correct decisions quickly, especially during abnormal conditions. I avoid clutter, use consistent navigation, meaningful colors, clear alarm priorities, and trend screens for key variables. The HMI should show equipment state, permissives, faults, manual controls, and process context without hiding critical information. I also design security levels so operators, maintenance, and engineers have appropriate access. Good visualization reduces downtime and operator error. While answering, focus on operator usability, alarm prioritization, color conventions, trends, equipment states, permissive visibility, access levels, security, and designing for abnormal situations and rapid diagnosis. Question 10. How would you troubleshoot communication issues on an industrial network? Industrial networks must be reliable, deterministic enough for the application, and easy to diagnose. With Ethernet IP or Profinet, I check device addressing, topology, manage switches, scan or update rates, and produced consumed data sizes. For troubleshooting, I look at link status, duplicate IPs, dropped packets, device faults, and controller connection diagnostics. I separate control traffic from office traffic when needed, and document every node, because network issues can look like logic problems. Make sure to cover protocols like Ethernet IP or Profinet, topology, addressing, manage switches, update rates, diagnostics, segmentation, latency, packet loss, and documentation for maintenance teams. Question 11. What is the difference between permissives and interlocks in controls logic? Permissives are conditions that must be true before starting. Interlocks usually stop or prevent operation when an unsafe or damaging condition occurs. For a pump, permissives might include tank level and valve open feedback. Interlocks could include overload, low suction pressure, or seal failure. I implement them transparently, latch critical trips when appropriate, display the exact reason on the HMI, and define reset behavior with operations and safety requirements. In your answer, define permissives versus interlocks, then cover latching, reset behavior, fault visibility, HMI messages, bypass control, safety implications, and maintainable logic structure design. Question 12. How would you structure sequence logic for a machine with multiple operating steps? A state machine organizes sequence logic into explicit modes such as idle, starting, running, stopping, faulted, and resetting. That is cleaner than scattered bits because transitions are controlled and diagnosable. I define entry actions, exit conditions, timeouts, and fault paths for each state. For example, a conveyor zone may wait for downstream ready before transferring. This pattern improves commissioning, prevents race conditions, and makes online troubleshooting much easier. Be sure to discuss explicit states, transitions, entry and exit actions, timers, fault paths, race condition prevention, readability, diagnostics, and why sequencing benefits from state machines. Question 13. Walk me through your commissioning process for a new control system. Commissioning starts before power is applied. I review drawings, I/O lists, network layouts, safety requirements, and vendor manuals. Then I perform point-to-point checks, verify sensor scaling, confirm actuator direction, test interlocks, and run equipment in manual before automatic sequences. During startup, I trend critical values and record changes with version control. The best commissioning plan is methodical. Prove wiring, prove devices, prove logic, then prove the process. While answering, outline pre-checks, drawings, I/O checkout, sensor scaling, actuator direction, manual testing, safety validation, trends, documentation, change control, and phased startup risk reduction steps. Question 14. A control loop is oscillating after startup. What would you check first? When a loop oscillates or responds poorly, I first determine whether the problem is tuning, hardware, or process dynamics. I check sensor noise, valve stiction, deadband, scaling, update rate, and whether the actuator is saturated. Then I examine trends around set point changes and disturbances. If noise is high, I reduce derivative action or add filtering carefully. Tuning should not mask mechanical issues. Stable control starts with reliable measurement and final elements. Make sure to cover process trends, sensor noise, valve stiction, deadband, saturation, filtering, derivative sensitivity, mechanical faults, disturbance testing, and avoiding tuning around hardware problems. Question 15. How would you approach upgrading a legacy PLC system with minimal downtime? For a legacy PLC upgrade, I start by capturing the existing program, drawings, I/O, network connections, and operator functions. I map old addresses to the new platform, identify obsolete devices, and plan downtime with rollback options. I simulate or bench test critical logic, then migrate in phases when possible. The biggest risk is undocumented behavior, so I involve operators and maintenance early, verify every field signal, and keep backups at each milestone. In your answer, focus on migration planning, backup strategy, I/O mapping, obsolete hardware, simulation, phased cutover, downtime windows, rollback plan, operator input, and validation testing. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.